Hi everyone, thank you for joining us for today's webinar, Advanced INS Setup for Challenging GNSS Urban Environments. I'm Jeff Besbrode, Marketing Executive here at OxTS, and presenting the webinar today is Sam Suleiman, who is one of our Senior Support Engineers. Sam will be discussing how to set up an OxTS INS to collect data in challenging GNSS obstructed urban environments. The session will cover several key topics, including the importance of GNSS related settings, GNSS weighting, GNSS control mode, and GNSS recovery, the importance of tracking multiple GNSS constellations, the use of SBAS, NTRIP, and RINEX corrections, and why it's important to accurately configure your INS and use tight tolerances. We will also talk about some other points, but these are the sort of main key takeaways. The presentation is due to last approximately 30 minutes, and there will be some time for questions and answers at the end. If you would like to ask any questions during the presentation, you can ask these using the drop-down menu, which is located at the bottom of the panel on the right-hand side of your screen. If you ask any questions here, we will answer them at the end of the presentation, and the webinar will also be recorded and a copy sent out to everybody who registered tomorrow. So without further ado, I'll hand you over to Sam.
Thanks, Jeff, and welcome everyone to our webinar. So as mentioned, the focus of this webinar will be data collection with land vehicles, specifically in challenged GNSS environments. So those environments where the GNSS signal is not, ideal, like in dense urban environments, for example. So we'll be looking at the role of the INS, what you would be expecting from it, the issues that can prevent an optimal output, and those settings that can allow you to obtain that optimal output from the IMU and the INS. So just a quick example of what we mean when we mention challenged GNSS, so that we are on the same page. This is a snapshot taken from New York City, and the trace that you are seeing there in light blue is the GNSS only trace, so not corrected by the IMU data. Basically, it means that you have a lot of obstructions and deflections, so either the GNSS signal doesn't reach the antennas in the first place, or it does, but only after having been deflected and bounced possibly several times off a number of surfaces. Could be metal or glass or anything that basically prevent you from getting a clean signal from the satellite, which obviously get in the way of having an accurate position. As you can see here, the trace is bouncing all over the place, and definitely it's not something that can be usable. So what does the INS do in this context? Very simply, it provides the navigation data that will be required to collocate the land vehicle and consequently all the sensors that will be mounted on the vehicle in the 3D space. So this includes time, first of all, so all of your data is synchronized to the GPS time. And obviously position can be in absolute terms, so lat, lon, alt, or in a local coordinate frame perhaps. Velocity and orientation angles, heading, pitch, and roll of the land vehicle, and again, consequently of all the sensors that are mounted on it. Another important aspect is the integrity and reliability of the data. So it's important that the accurate time, position, and velocity and orientation data is there throughout all of the data collection without gaps. This is what we expect, to get from the INS, generally speaking. So what are the issues then that can get in the way? 4 broad areas: non-ideal physical setup or non-ideal configuration of the INS, incorrect initialization, and incorrect or insufficient warm-up. We will go through each of these, what we mean with a correct one for each of these 4 aspects, and plus at the end, hopefully I'll have the time to add a few information that I hope you might find useful in your data collections. So let's start with physical setup first of all. We start with antennas. Obviously, these are the only source, in fact, of the GNSS data. One of the main sources for data that the system will use, to calculate its position and velocity and its navigation solution. So, in order to have the best possible chance to get a good GNSS data, you need to have the antennas properly mounted, meaning, first of all, with suitable ground planes. Ground planes will protect the antennas from getting the signal, a GNSS signal that is bounced off the tarmac. So getting to the antenna from underneath it rather than from above, as you would expect it to be. Another important thing is the antenna separation. This is for the accuracy of your heading solution. And that's why we use two antennas on our system, is it helps with the accuracy of the heading solution. It would be better to have it at least 1 meter separation. If you can afford more than that, and often that's the case on a land vehicle, then you can go up to 1.5 meters or 2 meters. Also, you need to pay attention to the sources of EMI, because the GNSS signal is very faint in nature, so it can be disturbed a lot by other sources of EM signals. Any device that you have on the vehicle, a LiDAR, cameras, radars, all sorts of things can be potentially a source of EMI. So it is good to have a think of where you place them, have them as far as possible from the antennas, especially the primary antenna, and keep in mind cables as well, because they can be source of EMI. So it is important to insulate them properly and also to route them away from the antennas and the INS as well. Another thing, in challenged environment where you know that it's going to be difficult to get optimal GNSS data, then it's always good to use higher grade units. So meaning with higher quality IMU and GNSS receivers. For example, for the OxTS line, product line, we can have the RT3000 or the Survey Plus units that are the best basically that we can offer, and those will have the best IMUs and GNSS receivers mounted on. Back to antennas, there are a lot of different antennas. There are higher grade ones, the one that will have embedded protection from multipath, or designed basically to handle multipath, which is the bouncing of GNSS signals all around, to handle multipath in a better way. If you can, you might want to use aiding devices, for example, a wheel speed sensor or other devices. We will touch on this shortly, that can help the navigation solution in absence of GNSS data. And another important aspect is having as many satellites as you can, considering that you know beforehand, because the environment is say, for example, a dense urban environment, that you will have, as we discussed, a lot of obstructions or deflection to the signal. So you want to try to get as many satellites as you can, meaning if you enable more constellations, you have a better chance of having enough satellites at any given time. And OxTS RT3000 and Survey Plus units are now full quad constellations, meaning they can track GPS, GLONASS, Galileo, and Beidou. So the more satellites you have, and like I said, the more likely you are to hold on to a higher quality solution. Just to give you an example here, we have a comparison between it's the same unit that was basically the data was processed twice, once using GPS only data, that's in blue, and the other using GPS and GLONASS. So roughly speaking, say doubling the number of available satellites. So what you see on the graph, the dotted lines are position accuracy, blue and red. Again, blue is GPS only, red is GPS and GLONASS, and the solid lines are position mode. So we can see how for most of this example, we can see that the position mode of GPS and GLONASS was at 24. This is RTK level, GX RTK, so the best effectively. While the blue one, GPS only, was just at GX diff, and that corresponds to very different position accuracies. You can see that in GX RTK, position accuracy is around 1.5 centimeter, whilst the GPS only, because it have very few satellites, it cannot hold on to the GX RTK solution, so it goes to above 30 centimeter position accuracy. At some point towards the end, you see that the system manages to hold on an additional GPS satellites and bounce up to the GX RTK level, where the GPS and GLONASS solution was all along. And in correspondence to that, you can see that position accuracy goes to the same level of the other one. The situation on the ground that corresponds to this is this one here. So the red line, again, that's GPS and GLONASS, whilst the blue line is the GPS only. So we can see that the red line is more solid and correct, traveling right in the middle of the road, whilst the blue one is jumping around. And that is all due to the lack of available satellites. So it's something that you can compensate for by enabling more constellations. So you have more satellites you can pick from. The correct configuration. So the first aspect is to set the exact distances, or lever arms as we call them, between the primary antenna and the IMU, and also the orientation of the IMU in the vehicle, so that you have a perfect alignment between the IMU and your vehicle. And this ensures that the directions, the accelerations, the angular rates that the IMU is measuring are in fact the ones of the vehicle. They are the same. In order to get that, you need a perfect alignment. So orientation of the INS in the vehicle and the lever arms between primary antenna and IMU has to be measured accurately. The ideal way of doing that is to do your best to measure those distances and orientation. Distances, say, within 10 centimeters, and orientation within 5 degrees. Do your best to do that, and then when you configure our devices, you can set a tolerance on those measurements, meaning how confident you are that your measurement is correct. So ideally, you would leave that loose to start with. Do not, overestimate how correct your solution can be. And then you do a full calibration run. We will go through this in a minute. So basically what happens here, that's the system will figure out the exact orientation and the exact lever arms for you if you do a calibration run properly. And then you can use the improved configuration tool that comes with the software, with navconfig software, to upload this improved settings to the device. An important aspect is that this warm-up or calibration run needs to be completed in RTK or PPK position mode. So you need differential corrections either in real time, that's RTK, or you can collect the data without corrections and then add them in post-processing. That's PPK. It can still work as long as you add differential corrections at some point, so that the position accuracy of the system during this calibration run is down to 1 centimeter. Like I said, we will go through the conditions under which you will have to complete this warm-up in a minute. Alternatively, if you don't want the system to calculate that for you, obviously you can do it yourself. If you are, for example, if your measurements are based on a CAD model, then you can be fairly confident of what all the angles and the distances are. So you can do it manually, and you can also tighten the accuracies or the tolerances manually down to 1 or 2 centimeters. Keep always in mind, please, that setting a tight tolerance on a wrong measurement is going to be worse than leaving a loose tolerance. Okay, so that's an important aspect. You will confuse the system. It will eventually understand what the situation is, but you will force it to lose some time figuring out what the real measurement is if you set a tight tolerance on a wrong measurement, because the system, initially at least, will believe you, will trust what you are saying. There is one measurement that the distance does not refine, and that is the distance between primary and secondary antenna. So this one you have to measure yourself, and you have to try to be accurate in measuring it. The distance is the 3D distance. So if, for example, the two antennas are not level, are not at the same height, then the distance that you want between them is indeed the 3D one, not the projection of this distance on, say, the level, if that makes sense. So measure that, as accurately as you can, and set the tolerances to 2 centimeters by default. If you are super confident, set it to 1 centimeter. Do not go below 1 centimeter, even if you are absolutely sure. It's always worth to have, some, leave some tolerance in there. So like I mentioned, in navconfig, there is the improve configuration tool, that the button that you can click on, and that will take you through the procedure of uploading improved settings that you can have following a full warm-up. And this is an example of what the automatic tool can do for you. So you start, from, say, round numbers, you see 90 degrees heading and so on, and the system will correct that, as you can see, to very small angles, a 0.24, say, angle, and also look at the level of accuracy. So you start from 5 degrees, it brings it down to, very, very small angles, 0.015. Same for primary antenna position. So that's the lever arm between primary antenna and IMU. You start, say, again, 60 centimeters, 15, 85, and it corrects it. It brings it down to, say, not 60, in fact, it's 56 centimeters and 8 millimeters, or from 15 down to 11, and so on. And again, it tightened the tolerance from the default 10 centimeters to 1. Same for the orientation, not the distance, mind you, as I mentioned, that will not be corrected, but the orientation, the alignment between the two antennas. You start from 0, that corresponds to the secondary being ahead of the antenna. It corrects it, and it points out that it is, in fact, minus 1.7 degrees nearly, with an accuracy, as you can see, that is very tight. Okay, this is what the system can do if you complete a proper warm-up in suitable conditions. Alternatively, if you wanted to set the tolerance that you consider to be correct manually, you can do that in navconfig, in the advanced tools section, accuracies tab. Basically, you set the measurements that you consider to be correct. Again, better be safe than sorry, as we say. So do not tighten too much. Just as much as you think it's correct, and possibly slightly more than that. So if you are super sure that you consider your distance measured, for example, to be accurate within 1 centimeter, perhaps set the tolerance to 2 centimeters. Okay, moving on other aspects of the configuration, the GNSS related settings. There are a number of them. First one, when you are in a GNSS challenge environment, such as an urban environment, it can be good to try the tight coupling mode instead of the loose couple mode. So what these modes we refer to sometimes as a receiver mode, whereby basically the position solution is calculated by the receiver, and this is integrated by the IMU solution, especially in those cases where you have GNSS outages. So that is referred to as loose coupling. The tight coupling takes both data from IMU and GNSS from the start, and it blends them together instead of having the IMU solution and the receiver solution, so to say, and then kind of average them or merge them together. What it does, it calculates one single solution starting from both GNSS and IMU data. So it's a much more tighter integration. We know, from experiments that we have done, that GXIX mode is better in urban environment. The aspects that makes it better are mainly the following. So first of all, it will not straight away believe the GNSS data, but it will check it against the IMU data. So any motion that is detected by the GNSS will be checked against what the IMU has detected. And if the same motion in the same direction was not detected by the IMU, the system would be very cautious in believing the GNSS. There is another settings that we'll talk about in a second related to this. So if the GNSS signal is bouncing around because there is a lot of multipath, for example, GXIX mode will be much more resilient to that. Another important aspect is that the GNSS receiver needs at least 4 satellites to fix a position. GXIX, and specifically the IX bit of it, can use fewer satellites, 1 or 2 or 3, can still use that GNSS data to help and integrate the IMU solution. So you can still have a position mode, a solution, even with fewer than 4 satellites. So basically, you do not go completely blind if you have fewer than 4, as it is the case with the receiver. Another important aspect is the relock when satellites are available. So if the receiver has fewer than 4 satellites available, it will have no solution. And then as soon as the 4th satellite comes along, it will recalculate its position again based on this available data. That is what we call relock. It takes time. It can take quite a number of seconds to do that. So even if you have those 4 satellites available, you won't have your position back immediately because the receiver will have to start from scratch calculating its position. In GXIX, because you've never completely lost your position, so you have some constraints, inertial constraints, what we call them. You are navigating based on the IMU solution. When the 4th satellite comes along, it will be much quicker in bouncing back to a full solution. It saves you time, and it limits the drift in your trajectory during that time. Currently, GXIX only supports GPS and GLONASS constellations. Whilst, as I mentioned, we can track and use 4 constellations when using receiver mode. So this is a limitation that we are working on, and we hope in the near future to support Galileo and Beidou as well as GPS and GLONASS in our GXIX algorithm, so to have full capacity. At the minute, what we have seen is, like I mentioned, even with fewer satellites available, GXIX can be, in several cases, better than receiver mode. To have it to its full potential, soon enough, we will have it supporting all 4 constellations. An option that you have, if you cannot make your mind say basically on whether to enable receiver mode or GXIX, is to select mixed mode. So that basically leaves it to the system to decide at any given time which of the 2 modes is the best. You do that, and basically you don't have to think too much about it. This is where you do it in navconfig, in advanced tools, GNSS control tab. These are the options. So GNSS receiver calculations, OxTS GXIX, and mixed mode, as I say. So I would recommend in urban environment, select mixed mode. Okay, and you leave it to the system to figure out at any given time which one is the best, so you don't lose anything in terms of the best performance that you can get at any given time. This is an example of, again, same data processed in GXIX and receiver mode. So GXIX is red, receiver mode is blue. This data was logged in Torino, northern Italy, and that was the direction of travel is from down here, bottom right corner, up, then turning left, and then coming back in again. So that was pretty much an urban canyon, very tall buildings, and a lot of multipath. So what happens is that the receiver solution, as you see, drifted, while GXIX, because it can work with fewer than 4 satellites, and also it has more resilience to multipath, you can see that the trajectory was much more sensible and steady, on track, whilst the blue trajectory was drifting, and only when we came out of this urban canyon, it managed to grab a few more satellites and, after some time, sort itself out and pretty much align with GXIX. So that is the kind of difference that you can have at times between GXIX and receiver mode. Okay, GNSS waiting and GNSS recovery. This is basically you are instructing the system on how much trust it should put into the GNSS data. So when you say there are some obstructions, so not open sky, you are instructing the system to be careful about GNSS data. And you say it's frequent obstructions, then you are instructing it to be very careful. So it limits the trust a lot in GNSS data. I would recommend to start with some obstructions, and then you can always reprocess the data. That's the good thing about post-processing, changing those settings. But like I said, frequent obstructions would limit the trust and consequently the reported position accuracy significantly. So you would have a position accuracy above 10 centimeters if you used frequent obstructions. Maybe that's not necessary. Okay, at times some obstructions would be enough. It's worth trying. And GNSS recovery, that's another settings that will determine, again, how much to trust the IMU over the GNSS. So when the two disagree, and it can happen, the trajectory calculated by GNSS can be different to the one calculated in dead reckoning, so using the IMU data. So what happens? Who should the system believe when IMU and GNSS disagree? You can have a say on that through these settings. You instruct basically how many GNSS updates, so solutions effectively, should be rejected before the system believes the GNSS. So imagine that the GNSS is saying something that differs from the IMU. The system initially will not believe that GNSS update. It will take it as, a multipath result, GNSS signal bouncing around. But imagine that same update keeps coming in again and again and again and again. How long does the system have to go before it believes the GNSS? How many updates it takes for the system to believe it? This is you can set. Okay, this is something that you can instruct the system to never believe it right away, wait a minute, wait 2 minutes, and so on. Again, this is something that you can change in post-processing and fine-tune it. There will not be a one size fits all. It will pretty much depend on specific data, like the situation, the conditions that you find yourself in that given day. This is in nav config where you can set the settings that we discussed. So again, in the environment session, you can set the GNSS environment, say some obstructions. Again, start with that, perhaps change it later if needed. And in the advanced tools GNSS recovery section, this is where you can select literally the number of updates that the system should ignore before believing the GNSS. The firmware default is 20 updates. Again, this is not seconds, this is updates. So it will depend on the frequency, the rate of your GNSS receiver. So if you have for example, 2 Hertz, that's basically 2 updates per second. So 100 updates, that's obviously 20 seconds. Sorry, 50 seconds. Okay. At the same time, because depending on what sort of device you have, you will have different values between position and velocity. On our T3000, for example, you would have 2 Hertz for position and 10 Hertz for velocity. So keep this in mind when you configure this. The two rates are not necessarily the same. It depends on the specific device you are using, and all of this information is easily available with your device. Okay, other settings that can help in challenged environment. The advanced lip. This will help to measure the exact alignment of the IMU to the vehicle. So it can limit the heading drift and consequently the position drift when you are in GNSS outage specifically, or in bad GNSS. You set it in the hardware setup section, lateral slip, and vertical slip. Okay, these are basically to ask you to select a point and specify where its position is relative to the IMU. The wheel speed sensor can provide an additional source for accurate velocity data. So when you are in GNSS outage and you cannot rely on GPS, the wheel speed sensor can help the IMU. You have a better speed velocity solution, and consequently you have a better position solution as well. And it's worth mentioning that with our new models, the V3 models, you can have quite a wide number of devices that you can use as external navigation aiding. You feed that data. It could be from a LiDAR, from a radar, from a camera, from other sensors. You feed that into the system through the generic aiding, as we call it. So you have something that can help the system out. The wheel speed sensor specifically can be configured in the advanced tools wheel speed input section. And just to give you an example of what basically the impact that having advanced slip and the wheel speed sensor can do, we took one of our data sets collected in OpenSky, so with good GNSS data, and then we blanked the GNSS data for 10, 60 seconds, 240 seconds. So we can see when it's a very short, basically, period of GNSS outage, there is not a real significant difference between having these options on, both on or both off. But look what happens when you have 4 minutes of continuous GNSS outage. So the system is blind for 4 minutes. You can see that when you have them both on, the drift in trajectory can be as little as 2 meters. Obviously, it will depend on the specific case, like what kind of motion you have during that. But 4 minutes of GNSS outage is really significant time. You are unlikely to have that unless you go into a tunnel, for example. But if you are driving in a city, you won't have 4 minutes of complete outage. So it's a very harsh, test, and yet the drift was limited to 2 meters. If you have none of it, you can see that the drift can go, above 100 meters. This again, the test was challenging. It doesn't get this bad every time. Every time you have 4 minutes of GNSS outage, we push the system to its limits, if that makes sense. So the motion during the GNSS outage was deliberately, challenging, confusing, with a lot of turns and corners and bends, to challenge the system, not simply driving quietly. Okay, initialization. So initialization is basically about getting directions right, literally. On a land vehicle, it's fairly easy to get it right. All you need to do is to drive forward in a straight line. So the things that you have to be aware of is just to have enough space in front of you so that you can accelerate to reach a speed threshold that will allow the system to initialize. And that speed threshold can be set. You can choose, what speed the system will initialize at. What we would recommend is to have it high enough, large enough, at least 5 meters, 10 is probably better, to ensure that you are actually driving straight when that happens. Okay, if possible, choose a level spot. If it's not level, no problem, just configure the system and tell it that it is not on a level. Another option is static initialization, whereby the system initializes thanks to the data from the 2 GNSS antennas. But if you do that, remember that because you are not moving, so the IMU, is silent, it's not providing meaningful data. The system is completely relying on GNSS data. So the GNSS data has to be good if you are initializing statically. So you need to be in an open sky environment, not in between buildings. If you have a correct configuration, then static initialization can be very quick, under a minute. This is an example of correct against wrong. So red again is the right one. Wrong is forcing the system to deliberately initializing wrong. In this case, I have initialized the system on a bend. So the system will take a bend to be a straight line, and consequently it will get its direction wrong. So you can see that the trajectory is wobbly. it's not accurate. That is because of a wrong initialization. Finally, the warm-up. Okay, this is certainly important to get your system to perform at its best. First thing to say is that we have a warm-up window of 15 minutes. So that is the time from initialization, from when initialization occurs, that you have to warm up the system. Generally, we say that you have to do 10 to 15 minutes, but in fact, it depends on how good your starting configuration is. So if it's a loose, not super accurate configuration, then we say 10-15 minutes. If you start from an improved configuration, one, for example, that you have uploaded through the improved configuration tool that we discussed earlier, it can take as little as 5 minutes. And if you are post-processing the data in combined mode, then it can take even shorter than that. So a warm-up has to be completed in OpenSky, and we recommend a varied motion. In a minute, I'll detail what that means. Again, you start from a tight configuration, 5 minutes is enough. If you start from a loose configuration, a bit longer. What we call calibration run is when, at the beginning of this webinar, I mentioned that you do your best to measure the lever arms and orientation, and then you leave the system to figure out what the real measurements are. So your configuration is not spot on yet, and you wanted, to get that. So you do a calibration run. This is a warm-up of the full 15 minutes, if possible, in OpenSky environment. Okay, then you use the improved configuration tool and you upload that configuration. The good thing about it is that you only need to do it once, unless you move stuff on your vehicle. But if the antennas and the INS is staying in exactly the same spot all the time and you are not changing that, then you only need to do the calibration run once. At that point, you will have your improved configuration saved on the system, and every next time you switched on the device, you only need a 5 minutes warm up, because you are starting from a very good calibration in the first place. Okay. In real time, if you want, you can monitor the warm-up progress using nav display. So it will, there are templates that we provide that can tell you what your position accuracy, velocity, orientation accuracy, and you can check how that is improving, as you go, as you progress in your warm-up. Motion types, just to say what we mean when you say varied. So basically, the key point is to excite all sensors, 3 gyros and 3 accelerometers. Straight lines at low speed and high speed, that's for heading. Accelerations, decelerations, that for pitch. Circles in both directions, that for roll accuracy. Figures of 8, that basically keeps it all together, and it helps also position accuracy. And if you can, some variation of altitude. This is not strictly required. I would say it depends on the environment you will be collecting your data in. Okay, so try to include the kind of motion that you will have during data collection in your warm-up. If you know that you are going to be traveling slow all the time, there is no point in pushing the speed during the warm-up to say 100 miles per hour, because you are never going to reach that speed, so there is no point. On the other hand, if you know that you will reach, say, 60, 70, 80 miles per hour, then make sure that that's included in the warm-up. Do not do a warm-up at 15 per hour and then you do data collection at 60. If you know that you are going to stop a lot, for example, traffic lights, then try to include some of that in the warm-up. Stop 30 seconds, and then move again, then stop 30 seconds, then move again. Try to match, to include as much as possible whatever motion you know you're going to have during your data collection into the warm-up, so the system learns about it. And again, do the warm-up in OpenSky environment. Once you have done the warm-up, you can go into dense urban environments, but only after you have completed the warm-up. Okay, finally, some very short and hopefully useful information. Datums and altitude. You have a few options to customize the output datum and altitude reference that you want to have your data in with our systems. You can use geoidal or ellipsoidal models, or even customize the geoidal undulation. If you have some models, some knowledge about what the altitude is in the specific area you are collecting your data in. You can have different datums, NAD 83, that's suitable for North America, ETRS 89 for Europe, WS 84, that's global. Depending on what exactly datum you want to refer to, you have a number of options with our systems, which can be useful at times so you don't have to convert that later. And you set it in the Advanced Tools Global Coordinate System tab in navconfig. Another useful tool is output displacement. So perhaps at times you want the data from the INS, position, velocity, orientation, and so on, not from where the INS is mounted, but from a different location, perhaps where you have mounted your LiDAR or camera and so on. So you can configure the system to displace the output to that point. All you need to do is specify where that point is in relation to the IMU. Okay, so instead of having the INS data from where the INS is mounted, you have it from a different location. And might be useful also to know that you can change this in post-processing. So you can, by running a few, processing the data a few times, changing the displacement output every time, you can have the data in a number of different points, if that is what you need. So for example, in the position of a number of sensors, if you have them. And finally, something on the differential corrections. There are a variety of them. So very quickly, SBAS, this is provided by satellites. It is free, but it's worth mentioning that it's only compatible with GPS satellites. So if you have more constellations on your system and you have SBAS enabled, those other constellations will not be used. So keep this in mind, because obviously you are limiting the number of satellites that you are using. Practically speaking, it would be as if you did not have those Galileo or GLONASS satellites, because SBAS won't make use of them. NTRIP corrections, these can cover wide areas. What you need is a good mobile internet connection, obviously, because if you lose the connection, you will lose the stream, the NTRIP stream, and the position accuracy of your system will suffer, obviously. If you can post-process, so we are not only interested in real-time data, but you are happy to post-process, then RINEX files is definitely a good option, because you can add differential corrections in post-processing, even if you do not have any corrections in real time. You just add them in post-processing, and you do not have problems of interruptions, in the stream. So that's an advantage that RINEX files will have on NTRIP. A downside can be finding a base station that provides RINEX files close enough to your test area. Okay, an important aspect is to specify the datum in which corrections are provided. Be it NTRIP, be it RINEX, this should be specified by whoever is providing the corrections. So by the organizations, say CORS, for example, that is providing those corrections, it will tell you what datum they will be in. In North America, that will typically be NAD 83, typically, not every single time. Okay, for NTRIP, this is where you enable it in the hardware setup section. You just tick the box, literally. There is also an option to use the internal NTRIP client on our systems. So more on that, you can send us inquiries about this if you are interested in knowing how it works. Or you can also set SBAS in the same tab. Just a word on post-processing. Like I mentioned, if you are not only interested in real-time data, then post-processing can be a very good option. It has a few advantages. One, you add differential corrections. Two, you can process in combined mode. I'll show you an example in a second. So that's forwards and backwards and not just in simulated mode, so similar to real time. And also you can tweak your configuration. So if your results were bad, by correcting the configuration, perhaps correcting the orientation of the unit or the lever arms or something else, the frequent obstructions, some obstructions, the level of vibrations on the system, there are all sorts of things that can be changed in post-processing. So you can modify the configuration and reprocess your data, and by tuning that configuration, you can have a better result. This sometimes, it's very useful. This is how we fix a lot of problems, by reprocessing the data by tweaking the configuration. What combined processing does is taking both the forwards and the backwards trace. So it goes, in both directions, and it takes the best of the two at any given time. By doing this, basically, it limits the drift, the inaccuracies of each traces. One thing that is worth remembering is if you know you are going to use the backwards processing as well, make sure that you do a very short warm-up, 2-3 minutes, at the end of the data collection, not just at the beginning, because that is the one that the backwards, that will start from the end, obviously, that is the warm-up that it will use. So if you know that you will need a combined processing, it's worth including a very short warm-up at the end. Again, 2-3 minutes will do it, no more than that. This is where you select it in NavSolve. You select just the processing mode, and this is a couple of examples to show you the difference between simulated and combined. So same data, just processed in 2 different ways. This is position accuracy, no corrections, that just SPS mode. So simulated is at 25 centimeters, and combined, as soon as both forwards and backwards are available, so this central section here, you can see that it goes down to 15 centimeters. Okay, just by way of merging together forwards and backwards, so they improve each other. Final example, again, simulated is position accuracy in blue, combined in red, and the green solid line is the number of available satellites. You can see that it is jumping between 3 and 6. So a harsh environment, okay, even going below 4, which, as we know, it's a critical threshold. So you can see that combined keeps the system at 1 meters. Again, no corrections applied. While the simulated is way worse, and the situation on the ground, again, New York City, you can see the red line is solid and sensible. That's the combined processing, while the simulated or real-time one was drifting, going over the pavement, then switching sides. By reprocessing this data in combined mode, you get a far better solution. Okay, thank you. One last thing I want to mention before, I know it's late now, but I just want to say that if you have any questions, you can always, send an email to support@oxts.com, or also visit our support website, where you can find a lot of articles and guides that can be useful. Thank you.
Thanks for that presentation, Sam. That was a really in-depth presentation. So I know we're running late, but if anybody has any questions for Sam, please feel free to ask them now, and Sam will do his best to answer them. We don't have any questions coming in, Sam. But like Sam said, if you do think of any questions after the event, feel free to email them in at support@oxts.com, and again, we'll do our best to answer them. Yeah, still no questions, Sam. So yeah, I think it's probably best to leave it here. But thanks very much for your time and taking us through that today.
Okay, thank you all. Have a good day.